Okay, sorry for the interruption.
Are you gonna take a tally? You could just like on a piece of paper.
Oh, I need to pass this out. Okay, so with this law of thermodynamics, okay, the second law of thermodynamics deals with this concept known as entropy. So let's define it and then I'll tell you the law. Okay, so entropy is first off symbolically shown as the letter S. Okay, I know it's kind of awkward, so that's what they chose. Okay, so S is the symbol for entropy.
That's how you know that's the first one I've ever seen in my life, right there.
Really?
Yeah.
It's a good day.
I know, right?
Okay. So, what entropy measures, everybody, is entropy is a measure of the disorder of a system. Okay, so it's really interesting that scientists came up with a scientific way, and there's a numerical value associated with it, that actually signifies how disordered or / organized a process is. Now, what's interesting is you can also think about is the dispersion of things. The more dispersed something is, the greater its entropy, or vice versa. With this idea of entropy, the second law of thermodynamics states that the entropy of the universe is increasing.
Slowly.
Wait, so everything is just...
So what does that, so don't say it out loud, turn your table, buddy, and what does that mean? The entropy of the universe is constantly increasing. What does that mean? Ready, set, go. No. That's where you have to search your soul, because everyone believes differently.
Actually, the Earth is the center of the universe. Back off.
Yeah, you want yourself, sir.
Yeah, flat Earth for life.
It is a good question.
Just flat, though. What's on the other side? It is like a second Earth.
The Earth
I'd have to
is
bring
flat
you
Earth
some
for
more to try to answer that.
Oh,
Just like thinking about
oh, that's really fun.
Alright, I'm going to pick on Taylor because I heard him somehow. Just kidding.
I'm kind of loud. I'm not gonna lie.
Okay, Taylor, what did you say about this idea of the second law of thermodynamics?
I just think the universe is getting more spread out.
Yeah, so one, which we know the universe is expanding, falls in this same path. It's just an interesting concept because we know energy has to be conserved, but entropy doesn't. Entropy continues to increase, and things naturally increase in entropy. So literally, you can use entropy to blame the messiness of your room. It's entropy's fault.
It's entropy's fault. Mom, it's entropy's fault. You best watch yourself.
Yo, if you tell your mom to best watch herself, I will drop you.
We're probably going to do that. But,
Yeah, no.
but it is an interesting idea. To us, it's just natural because it's the way we see the world. But if you think about it, it is interesting how things just naturally get disordered or dispersed. They don't do the reverse, right? When you mix two things together, unless there's a force keeping them apart, they blend, right? They disperse between each other. They just naturally do it. You don't have to do anything to make them happen. They just do it, right? If I have an air freshener, it naturally fills the room, right? It doesn't just stay in its little corner.
That's so cool.
But I mean, to us, it's like, well, yeah, that just makes sense, but that's kind of where
You
this
don't even,
idea of
like,
entropy
think about
comes
it,
in.
though. You know, like
That's so eye-opening.
Every day I blame entropy for my desk. Because at the beginning of the school day, my desk was very organized and clean. And then every day I have to clean it again. Same thing like with your room. You're probably like, why do I always have to clean my room? Right? Because entropy just naturally dictates the room. Okay? So let's take a look at molecules here, everybody. And predicting whether, looking at a process, one of the things you should be able to do is predict whether entropy is increasing or decreasing. Now, really, you just have to visualize these things at the molecular level. Okay, so for this particular example, the delta S is going to be negative. Okay, so put a little negative over there. Now, negative entropy means it's getting more organized, is like a metaphor you can think of, okay, or it's getting less dispersed. So for this one, it can be explained by the left side of the equation, you have 3 separate molecules. On the right side of the equation, you have 2 molecules. That decrease in number of molecules is more organized, and so that's why entropy is going down.
So this actually isn't that complicated.
It's not, no, it's really not. Entropy is actually like a pretty logical thing. Most of the time we just never really know it was a thing. What is interesting though is when you get really down to the molecular level, is molecules and atoms move in a lot of different ways than what you maybe have visualized before. And we can refer to these motions as their degrees of freedom. The more degrees of freedom a molecule has, the more entropy that exists. Or if you decrease those degrees of freedoms, then entropy goes down.
So like if 3 became 2, but the degrees of freedom went down like super much, could the entropy possibly go up? Or down? Or whatever the opposite would be?
So like in this picture you're saying?
Yes. Let's say
Go ahead.
NO has, I guess, way more degrees of freedom than N and O separately do.
Yes.
Could the entropy in theory like go up?
Theoretically, I guess.
Okay, got it.
I would say generally though, whenever you go to less number of things, or I guess a better way of saying, when more bonds are created, you lower the degrees of freedom.
Okay, yeah, that's a
Now, with these degrees of freedom, it all goes into the motions they are able to do, right, through dispersion. Now, with these motions, there's a lot of different ways molecules can move, and I know you guys will be really excited about this because I have a new dance to teach you.
Yeah.
Okay, and now that prom is happening, you can all do it at prom, and it's going to be awesome.
Yeah.
Okay, so here's, ready, pretend with me here. See, so I'm a water molecule, okay? So
I am a water molecule.
well, you don't have to do it with me, but visualize, okay? So my heart is like the oxygen, okay? My hands are the oxygen. Everyone see the water?
Yeah.
Because water is bent, right?
Yes.
Okay? Now what we may not realize is a lot of times we visualize molecules as bouncy balls, right? At least that's how I think of them moving around. But within those bouncy balls, they can do a lot of different motions, particularly the bonds. The bonds within an atom aren't these solid sticks that we sometimes make them on pictures and models. They can move in all these different ways. They're known as the vibrational moments. So the water molecule can do this, right? It can do this,
I'm gonna hit someone.
and it can do this,
Oh, I like this one.
right? Okay?
This is like-
So those are all considered vibrational motions of the bonds themselves. At the same time,
Oh, you can spin
the
around.
molecules also can rotate. So you have vibrational
Oh, this
and
is like this is like the
rotation.
equilibrium dance on like
Steroids.
on
This
a
is
lot
like the what?
the equilibrium dance on
Oh, yeah,
steroids.
it's pretty intense.
It's on roids.
Because then at the same time, they also are translational, meaning they're moving through the
So
air.
you jump up and down too.
So at the same time, so you got your vibrational, your rotational, and your translational.
Die.
Yeah. This is gold.
Imagine with me, right? If everyone is doing all those motions at the same time at prom, what's the entropy described as?
Pretty high.
Yeah, crazy high, right? So as you reduce these types of motions, entropy gets less and less. Primarily, think for an example, if I change something from a liquid to a solid, what type of motion am I getting rid of?
From a liquid to a solid.
Translation.
Good, Evan. Yeah, there's no more translational when something's a solid, right? These things are still moving because they're vibrating.
So they're just like doing this.
Yep, so we could see inside the table.
Are they spinning too? Or is that?
I'd say most rotational's gone too when something becomes a solid.
So maybe they're just like.
Yeah.
It's like the Deacon two-step, but for molecules.
The people who are embarrassed, right?
You
They're
don't
only
know the
the big
Deacon
one.
two-step?
So is absolute zero when all that stops, or does
Oh
it
my
go under
gosh,
that?
Evan,
Zero, Kevin.
you're a genius. You just said the third law of thermodynamics.
Wow. Sick.
So the third law of thermodynamics states that at absolute zero is when entropy is zero. So the only time entropy is completely gone is when you take away all movement. Yep. So that's Great
Yeah,
insight.
Evan,
Oh.
you're too good.
See, then that's what gets really weird is the fact that they went below absolute zero, then you're like, what does that mean?
Wait, what the?
They got it.
How's that work?
My blade breaks. I just
I've
want
never
to
used
know.
it.
Put that in absolute
Yeah.
zero. Do you like just
It
like,
is in the jar.
is there an
I
absolute zero
put it
question
in
in
there.
there?
I think there is.
Yeah, no, there's an absolute zero question about.
Do it just in case.
Just in case.
Yeah, I put another one. That's
And then it's more likely to find, so then if we don't get to zero.
So, with this idea, once again, going off with what Evan said, and this idea of producing movements, right? A gas, a liquid to a solid affects all those degrees of freedom. So this is pretty much how we explain entropy at the molecular level. Okay, so in a second here, we're going to bring it to the mathematical side of calculating entropy, but it's really important to understand what's going on and why entropy is going up or going down. So, for some smiley faces here, oh, I guess we have one more thing to fill in. Let's go with these things first. So, in general, what we see here is that entropy is expected to increase whenever you go through a phase change between a liquid to a solid.
What does that second one say?
Gases is what that one says. So gases always have greater entropy than liquids. And then the other one is the number of molecules. So the more molecules you have of gas, the greater the entropy will be. Okay, everyone good there? Okay, I'll give you 1 minute with your table buddy to identify for A, B, C, and D if the entropy is going to be positive or negative for the process as written.
And so positive is, oh, okay, yeah.
Positive is more
Yeah,
discrete.
Yeah, more
from
discrete.
like here.
Okay,
Yeah.
go talk to your table buddy if you want.
You know.
Just put a positive or a negative sign
So
right
it's
there.
positive. Then the next one is going to 1. So that's and it's going to a solid. So that's even
Solid and gas.
So that's good.
And then that one is
Solid gas.
gas, gas,
4.
gas. So there's no change there. And
Give me a
then
pencil
also
drop when you're done.
So this is going way negative. And this is 3.
Wait.
Oh,
but it's going
I would assume it's just
well, wouldn't it be the same amount?
I don't
Because there's bonds there and then bonds there.
I put negative, but now I'm doubting it because it does have more shape.
maybe it would increase because it's always increasing. I doubt that.
Right? More degrees of motion means higher entropy, right?
Yes.
Because now it has 2 arms instead of 1. That would be more movement, right? Yeah. Oh, you're right, because that's just 2 arms. So it's gotta go down. It's gotta go down.
But why would it go down?
Because it's more organized.
Well,
Because
so
science. You're right.
not like the size, it's like the amount of
What did it state?
so this one has 1, 2, so on this side there's 2, and then the product. So it's like going from like
Okay, wait, what do you guys have?
and then cutting it. No, it would be less because it's
Or cut half the amount of molecules.
Yeah.
the
Oh, that's a
amount of
good point.
molecules. So it's so there's a lot.
Oxygen's like double that, so it breaks 2 bonds.
So it's
What?
Yeah, how many bonds does, and,
So oxygen has double.
so it's just like less because like earlier when we
oh wait, I think it's
like
gonna
this
go down.
it goes
Because it breaks so many bonds,
goes
it has like 3 with nitrogen and 2 with oxygen.
it's kind of
Does that
like
make
that.
sense?
So it has
I'm not
less
sure.
bonds.
Okay, come to a final conclusion in the next 10 seconds.
I read pencil drawings.
Entropy is how spread out
Yeah. Like, I guess it'd be more, it'd be better to say it's 0. Would be more like, yeah, if you think it doesn't change.
I think it goes
It
down.
definitely changes.
I think it's more.
It definitely. Yeah, it's probably even better.
Yeah.
Yeah, she would never, probably gonna be never.
My favorite phrase. You're on the right
But you're not
Yeah.
supposed
Just
to
say
all
that, you're like,
know.
oh, you messed up.
Okay, give me a thumbs up for positive.
She said that.
Okay, thumbs down for negative, and fist if you're saying it's 0.
I always feel
Okay.
bad, like when the answer to a math problem is negative, because I just feel bad for the numbers that they're negative, you know? It's kind of weird. I'm like, it's just like,
I think that
it's so weird, you know?
Yeah, but which would you
I always want
rather
the answer to be
negative numbers or
positive.
But maybe you should relate more to science, because a lot of times negative numbers in science aren't a bad thing.
Yeah, what the heck, Taylor?
Like negative sadness, that's not a bad thing.
Yeah, but negative sadness is like a double negative.
But
Yeah.
like negative entropy is not bad, because that means your room is clean.
Yeah, but if when Spanish, double negatives just emphasize it even more, right? So if I
So confusing.
So if I'm negative sad, that means I'm just so depressed.
Yeah.
So
But only in Spanish.
yeah, in Spanish you
You would
emphasize.
say, like,
So if something's
no.
super good, you say it's like
Wait,
good.
so
good. I know.
in
That's what
Spanish
my brother says. He
math,
speaks
does
Spanish.
a negative, wait,
I
just
should
two
go with-
negatives, just, wait.
I mean, ask me. I'm
don't
curious.
have
That means Portuguese is
nothing.
probably the same too.
I feel like so you have something.
I wonder if like all the romantic languages fall into
Yeah, 'cause I have to watch over.
Like French
sometimes
and
it's
English.
Just give us two.
It makes sense because I'm like saying.
Wait,
oh, I
so like,
Okay, here we go.
let's say like,
Back up here.
As it is.
Well, wait, no.
Oh! And I just, that was louder than I thought. Okay, show me, sorry. Okay, thumbs up or thumbs down is
That
the
counts.
process
That definitely counts.
increasing or decreasing in entropy? You give me a thumbs up, have a smiley face, very good. Okay, letter B, show me positive or negative or no change. Very good, everyone is thumbs down, it is decreasing in entropy because you're becoming one thing and that thing is solid also. C, show me your vote. Good, it is decreasing as well, you're going from like what, 7 different molecules down to 2 and it's only a solid, all the gases are gone. Yes, for each one of these you can have a smiley face. Okay, and then show me your answer for D, everybody.
Whoa.
You gotta go positive, dude. He's got the double positive. He's sure.
Positive.
I'm not sure.
I'm positive it might be positive, maybe.
All right, now for this one, I maybe shouldn't have put it on. It is a tricky one. With as it's written, first off, and if you recognize that it's tricky, have a smiley face.
Yeah.
Why is this one tricky?
Because it's the same number.
Yeah. So first off, if you had to make a prediction, it's going to be very close to 0, right? Entropy is not changing a ton. Now to get the actual number truly, you kind of just need to know more of the actual values of entropy, which we'll look at here in a second. I like the logic I heard across the room, though, of trying to think about in terms of those degrees of freedom, right? If you look at the bonding of them, and you know what motions are going to change, if any. So nitrogen, right, is triple bonded to itself. Oxygen is double bonded to itself. And then we're making 2 NO molecules, which are,
I don't even know.
I don't know either, off the top of my head. Are they triple bonded? Double bonded?
Somebody Google it.
Or dude, you'll lose your ability if you take your phone's out.
My phone's not out. Your phone's out.
Your mom.
Yeah. Ah.
Oh, whoa.
Too far. Oh no. Stop telling. It's scary.
Okay, it's a double bond.
Ha. Google.
So we look at it this way. So you're breaking one triple. So by the way, too, for degrees of freedom, triple bonds have very little motion.
So I got it right. Okay.
Because when you're bonded 3 times, it really limits how much of this stuff you can do, right? Single bonds can move a lot more.
If your arms are tied together.
Oh, it would go up. Frick. No.
Imagine getting a.
Yeah, just to kind of show
You're
you, like,
stinky.
with our models and stuff, right? Is like, because when something is double bonded, there's an example, right? It limits, like, being them to rotate and things and stuff. So I would predict I don't even know the answer that I just said is it's pretty much 0 is what I got this in the book for this practice problem. But based off this, I would say it goes, because we don't have a triple bond, which is low in entropy. So I'd say it goes up a little. What I would predict, but
If we said it stayed the same, is that incorrect then?
no, I would say not. Because once again, being that I don't see them asking you this without giving you more information. So
Okay, but if you got it right, can you just smiley face?
I already gave you a smiley face for it, right?
Ah, cool.
Okay.
But I still got it all right.
Let's take a look at the
We're
math
basically the
side.
same here.
Yep, except I'm just more
Wait, is entropy the ones where it's like the tables with the bond value?
What was that, Gavin?
No, that's enthalpy.
Oh, enthalpy.
Hey, that's gonna come in here real quick.
You do the math.
Like the bonds, like where the bonds each have values for how much they can break them or whatever.
Yes. So similar to enthalpy though, what Gavin brought up is entropy has values. So scientists have calculated, so entropy is a unit of energy, so it's measured in kilojoules. It is important to recognize that entropy is extremely temperature dependent, right? Because obviously if you think of gas, liquid, solids, depending on the temperature of the room, changes in entropy of something drastically. So the entropy of things has been calculated, and so one way you can find an overall change of entropy, so put this in this box right there at the top, is you take the sum, so that's the summation sign, of the change in entropy of the products minus the sum of the change in entropy of the reactants.
Oh wait, yeah, so it is just.
And it's the exact same equation that we did for enthalpy. It's also on your formula sheet, so you don't need to memorize it. It's pretty straightforward. There's a box at the very top that says delta S of the reaction. Oh, let's define once again this little degree sign though right there, just as a reminder. Anyone remember what that means? It's been a while. It just means we're under standard conditions.
Is that 22?
Wait, really? That's what they mean? That's what a degree sign means?
Not
Oh, just this kind of.
in this setting, yeah. But it's like we saw with delta H, we can see delta H naught is how you say it.
Not. It makes you sound super fancy, like a boat person.
What?
Is that it? No, don't give us a dash for saying boat.
Wait, let's take a look and use this
I guess it
problem
would be fair though.
for this,
Go
or
ahead.
use this equation for this problem. Now, the nice thing is really, you know you're only going to use this equation if they give you a table of values. Otherwise, you can't use this equation without knowing the values individually. Now, on your homework assignment tonight, I didn't give you a list of values because there's a giant list of values in the back of your textbook. Appendix C, I believe it is. And I noted it on the problem of saying use the values in Appendix C to do this, okay? But all we're gonna do is the sum of the products. So NH3 is my product, so I find its value, which is 192.5.
But there's two of them.
Good, so then you gotta multiply that by 2, okay? So you're gonna draw some arrows to remind yourself where these numbers come from. So the 2 is because 2 in the equation, the 192 is just from the table. So then minus all the reactants, so nitrogen is 191.5. And hydrogen, we gotta do 3 of those. Like so. Questions on any of my setup? Now, without even solving it, let's say this was a multiple choice question and you're running short on time and you're like, I don't have time to do this without a calculator. You should be able to always estimate at least the sign of entropy, right? So from the equation, the sign of it should at least be what?
Negative.
Yeah, it should be negative. When you plug it in, I got negative 198.3. Any thoughts on what my unit would be with this?
Mole degree K.
Joules per mole. Okay.
You're kind of close together.
Joules per mole degree K.
So they're looking up there and those are like, where are these units from? So the units of these numbers is that, but one of those units gets canceled out in our math.
Oh, the moles one.
Moles.
Why?
Because we wanted it to.
Is
Oh, we did
So
the
is it
multiplication of the
joules
2
per
and the 3
kilojoule
and the
or
1.
three or more?
This is 3 moles of it.
I was actually right this time.
So the unit is just joules per Kelvin.
I was gonna say that as a string, but then.
So, questions on this equation?
Wait, why is it
Too good of a
only joules over Kelvin?
JK
Because,
Rowling.
so the moles in it gets canceled out when you multiply it by that number.
JK Rowling.
Oh, cause it's
Because then you get
Because it's like, so yeah, so this, if I have, so this was really, if I write out the units, this is 3 moles times
divided by
by
moles times
130
So
joules per mole,
multiplied by the moles of the two.
like that.
You get that.
So the mole cancels out, if you're multiplying it by it, so, good clarification though.
Wait, but then wouldn't there still be a mole from the one that, oh, cause it's times 1 technically. Okay.
Yeah.
We're chilling, we're chilling.
Way to answer your question. Any other questions on this equation? Okay, now we've talked about the law, second law of thermodynamics states that things will naturally, on their own free accord, get more disordered. Okay? But there are situations, I want you to see if you can think of one, where things naturally get more organized. Can anyone think of an example of something that naturally gets more organized?
freezing freezing water.
Perfect, that's my case. So freezing at the right temperature naturally gets more organized.
Magnets, like there's
Whoa.
like liquid magnets that
Yeah, I didn't even think of that one. Is that good? Have a smiley face for that. Bryce, did you have a different one?
No, I was gonna steal it because I heard him say that.
Oh.
I can do it.
Just thought you could raise your hand a little faster.
Like
Gabe?
if you cool something, like lower the temperature of it.
Yeah. Yeah, I mean, just in terms of that, when it gets cooler, those degrees of freedom go down, right? So what's interesting here is there's another factor that goes into play whether or not something happens on its own, in its own free will. And we have actually a measurement for this free will, as you would call it, known as Gibbs free energy. Evan, did you have another thought, another example?
Well, I kind of forgot.
Oh, sorry.
Gibbs from NCAS.
Who's that?
What? Shame.
All right, let me know when it comes back to you.
Okay.
Carly.
Just thinking about like the neutralization of like gases and gases, like would that be like more organized? Like once they're like less like positive and negatives going around, like they become more neutral, would it be more?
I would say so. Yeah, I would say it's getting more organized. Yeah, good example. I was my spot. Zach.
Would gravity be one? Like the solar system like pulls it in, makes it
Ooh,
more organized?
I don't know. I've never thought about gravity in relation to entropy. Is gravity going against entropy?
What is gravity? What is, that's the real question here.
I don't know. We might need to call up a physics teacher to combine our brains for that
You
question.
take AP Physics next year and we'll find out together.
But gravity
Wait,
is so complex.
Next year, come back and teach me.
Yes.
Wait,
I don't know, Zach. I'll have to think about that. That's a really good
B6?
thought, though.
No, like A, B, or B.
Oh.
Did you remember your question, Evan?
Okay, I will tell you after.
So I don't really know if this is true. It's kind of like a half question.
Okay.
But would like decreasing pressure increasing pressure or decreasing volume work, or would it just stay the same because it's like the same?
I'm glad you bring that up. It does in a sense, like if you increase the pressure of a system, it is going to force it to get more organized. But what's important to recognize about that is that doesn't happen on its own free accord, right?
Oh yeah.
So it's something we're doing, we're applying what we can say work to the system to get it more organized.
Okay.
Does that make sense?
Yeah.
But that's a great example of like the opposite of how we can get things more organized if we apply work to them. Right? Like I can get my desk more organized if I do something to it.
Yeah.
But there are some situations where things do get more organized without us having to do any work. They just naturally tend that way, and it's because there's more than entropy that plays into it. So this idea of Gibbs free energy is it's the energy that is available to do work. For example, batteries are full of Gibbs free energy. Right? You just put the battery in and it gives you energy out. We'll talk more about batteries actually next time's lesson. Max, why did I never think of that before? I've taught this for years.
What did you say?
Okay, say it again.
It gives you free energy.
Oh, that's pretty smart, man.
Gives you. That
Wait,
is
did you-
really smart.
Wait,
I don't know,
did
I
you-
never thought of. Did
I
ever
have to
catch
tell
what he
Tyler
said?
about this. I'm gonna teach there's a law named after you.
So it gives you free energy, right? So when something has, it just gives it to you.
It's a pump.
Gives it to you.
Some of you still don't. Maybe just don't appreciate it. So what we call is that when a process or reaction releases this free energy, we say that it is thermodynamically favored. And I know it's quite a mouthful. But what that's saying is, once again, is that it happens in its own free accord. Gavin?
In the notes it says when change of G is equal to 0.
Yes.
Are we supposed
That's
to?
why I highlighted it, is because I found that typo this morning. So change this on your notes, because it says equal and it's a really bad typo because it messes up the whole, pretty much everything we're talking about. Change it to less than.
This is what the laws of nature.
Yeah. So when delta G, which is Gibbs free energy, is less than 0, it means that that process is thermodynamically favored. Now, I have a question for you to ponder. Don't say it out loud. Okay? Here's the question. Don't say it out loud, just think in your head. Okay? Gibbs free energy is the amount of energy to do work. Okay, so if our equation has negative 200 kilojoules, that's the amount of energy to do work. Why, though, is it negative in sign? Don't say it out loud, just think in your head for a minute. So that's what it means. Why is it negative? Okay, turn to your table, buddy, and share with them your thoughts. Go.
I don't know.
That's kind of what I was thinking.
Like the article where
Since it's 0 or whatever,
it's
it's
talking
like
about entropy becomes smaller.
That's taking up less space.
Or also how
As a teacher, it's hard. You have to try to listen to your conversation.
It's like very
I think the reason it's negative is because humans chose to make it negative. You know, it could have been positive because it's like positive.
It's like a negative.
Yeah.
It has nothing to do with science. We chose to make it.
And maybe it's
Yeah.
talking about like,
I'm sure they had a reason to choose it.
and it's just like this,
Yeah.
like it's not talking about the number, but it's big.
Okay,
But it was. It's
coming
fine.
back up front here. Bryce, do you mind sharing your thoughts on this?
So I said because it's like, it's kind of being like used up to do the work, so it's like being like given and then used.
Given.
Good, yeah. No, it's like, it's how, because once again, you need to understand that there's no such thing, like tangible thing, as negative energy. Right? Like, just like there's no such thing as a negative dollar bill. I can't hand you something that says, here's a negative dollar bill.
Give me a real dollar bill back.
You can have a negative bank account. What does that mean?
Theoretical dollar bill.
Yeah, it's the direction in which these things are going. So when we're referring to that delta G, when delta G is negative, a process is thermodynamically favored, it's because that energy is available for you to use. We can use that energy because it's coming out of the process in the end. Okay, so what we're going to look at now is we actually have a few different equations. So the first one will fill in. I think there's a box. Is there a box to be filled in?
Yes,
Yeah.
there is.
This should look like deja vu here. One way you can calculate delta G is by taking the sum of the products minus the sum of the reactants. Alright, if you just figure out the overall change of what it's going to or coming from, you can find the overall enthalpy transition. Oh, Bryce, have a smiley face, by the way, for sharing your thoughts with
What
us.
a genius.
Now, everyone can earn a smiley face by solving this problem.
Okay, we got this.
Okay, so with your table, buddy, try out exercise 9.3A and B. Ready, set, go.
Okay.
And there's two separate smiley faces.
Yes,
4,
two separate smileys.
negative 2. Wait, but is it negative? Do we leave it negative?
I think it was
Would we not do the negative? Because that will cancel out and it'll be like crazy. But I guess these are really little, so maybe it would make
Okay,
sense.
so it's, do you have a calculator?
I have a calculator.
Well,
You don't get it, use it.
that's what I thought, I knew you were gonna say that.
You don't have it.
Privilege.
2.
Whoa.
Set your pencil down when you're done. You can solve A and B.
Would it just be?
I got negative, what, 1?
So, would we use this negative or would we switch the sign because that's just the
Negative.
so it's negative because it's fake. Yeah. And
So then if I do the reaction in reverse,
It is joules.
No, that was for the different
Oh,
one.
you're right, it's just joules.
so for this one we would switch it. Okay.
yes,
Okay.
yeah.
That took me.
Yeah, we haven't even done any work for this, we've been reading.
Oh, wait, I know.
Can you calculate it?
Oh, thank you. I think I have.
Yeah, yours is probably better than mine.
Okay. Thank you.
Is,
I think it died last period.
Oh, man.
unfortunately.
it would be 3
Alright, I'm gonna give you 1 more minute.
That is the same. So if you flip the equation, then it ends up being the same.
Don't forget your units.
And this would be
This one is not. Because the more.
Okay. So 7? Okay, so really good. 6 and a really good. Yeah, like a weighted version. That's good job. No, that means you should have said.
I weigh 180.
It
I don't
is,
think
I think it is supposed to be square. It's still
I
like,
probably could do
it's
it.
like, it looks like an E. Yeah.
With the internet?
Oh,
yeah, easy. You're God. No, not with you. Oh,
It's like
Oh, sure. You know, if I would have done
Yeah.
Yeah, I feel good. Maybe we'll put a chair on
So would it
that.
just be negative 1054?
well, because we need one really good one, so.
Yeah, it has to be a really good push-up.
Oh, yeah, diamond push-up. Or flat push-up.
Or netherite push-up, maybe?
What's a netherite
Maybe
push-up?
I-
That's where you
That'd be so heavy. Dude, chainmail is so freaking heavy. What?
Okay, write down your answer in the next 10 seconds.
We're gonna get this wrong because that's just how it comes to works. You know, like we think we all did it right, but actually we all did it wrong.
I
I
almost
got
did it.
10
There's no way you'd have that many smiley faces if you're doing everything wrong.
That's true.
You'd have to do at least something.
But like, what if you?
Who has
tricked
more?
us?
I have more.
Obviously, I'm trying to trick you.
By 3.
Yeah.
Hey, I've gotten quarantined twice, so.
I haven't used
So-
it. though.
Maybe.
I haven't used
How many
it.
classes I've missed?
I haven't used it.
So you have
You're good.
Okay, if you have, for part A, negative 1,102.8 kilojoules. Have a smiley face. And then for part B, if you have the positive value of whatever you had on A, you can have a smiley face.
Oh, so, so even if you
What
got
do we
A
have
wrong.
Because it's right, that's how I did the test, right?
Wholesome.
So
Also.
I walked around and I'm pretty sure everyone had it right, and if you had it wrong, I think it's just typing it in.
Yeah.
Any questions on that problem though?
Calculator skills.
Pretty straightforward. Okay.
Your actual math skills.
Alright, let's look at another equation for delta G. So this is on your formula sheet, so is this next one. Okay? So another way we can calculate delta G besides just the overalls is by looking at entropy and enthalpy independent of each other. So delta G equals the change in enthalpy. So just a reminder, enthalpy is delta H. Enthalpy is like what we refer to as heat. Right? It's the idea of if it's exo or endothermic. Okay?
Wait, that, oh, okay. I thought that was a whole equation.
No, I just
That's pretty easy.
You're like, it just equals that. Minus the temperature
It's gonna be added as minus the negative log.
times the change in entropy.
Well, I mean, for the ones off 27.
Keep writing things.
Okay, so the overall free energy of a reaction is influenced by both its enthalpy and its entropy. They both play a role in it. This is what helps explain why some reactions will naturally get more organized. Is because if it's exothermic enough, that exothermic process can be used to help it get more organized, or vice versa. So what we're going to do is we're going to look at a table here that compares all the different scenarios of enthalpy and entropy, and then the effect it will have on delta G. Now what I want you to do though is, because once again, we don't have much space in our brains if you just try to memorize everything in AP Chemistry. So don't memorize this table, rather understand where it's coming from so that you could, once again, come to the summary on your own. So, first example, I'm going to write this equation here so you can refer to it.
Don't say my mom. I will smack you.
So, let's say I have a situation of a reaction that is exothermic. So that means delta H is less than 0. Okay, so I have a process that's going to release heat, and it's going to get more disordered.
Why are you making fart noises? What is this?
So, if you think
That's
through these pieces individually, what does it mean for a process to be exothermic?
It
Good, heat is being released, which naturally goes to, well, if heat's being released, then energy is being released, right? We also know from the second law of thermodynamics, do things naturally get ordered or disordered,
Disorder.
right? So both of these things lean on the side of they just are what's going to happen. So if you have these two conditions together, you have a situation where it's always favored. These types of reactions are favored no matter what the temperature is, meaning that they're thermodynamically favored, they just always happen. Can anyone think of an example of something that regardless of how hot or cold it is, that process or that reaction will always happen? It's kind of a tricky one, but.
I mean, no matter how cold it is.
Someone said that last period too, which I thought was an interesting thought, but if it did get cold enough or hot enough,
You would melt. That's a good point.
you know.
And our chart, it doesn't say reaction characteristics, it says change of G is less than 0.
thermodynamically favored at.
Oh, I just expanded more of what it means.
Oh, okay.
So this is saying, so it's for this situation, right? If these are always true, it's always going to be less than 0.
Oh, so it's like when it actually makes sense instead of this weird.
Yeah. So delta G is always negative. Pretty much if you think of it mathematically, right? So if this is negative, I plug it in here.
Oh, yeah.
Delta S is positive. positive,
And it's zero.
right? No matter what these numbers are, the end result will always be negative, right?
Yes.
Something with the symbols, I saw this on a chart, so if it helps you, they just kind of compared and said, well, like, how the symbols were. So when the symbols are facing each other, it's always that way. If we go to the reverse and say, let's look at an endothermic process. So an endothermic process that gets more organized. Let's see, so more organized would mean entropy is going down. Oh, wrong direction again. No, I did that right.
I was like, you guys.
Okay. So in this situation, it is never favored. Meaning no matter what temperature you do these reactions at, it's never going to give energy out. Just doesn't happen. To make these types of reactions occur, you have to put the energy into them. Okay, so we have an always situation, a never situation, so our next two are
Sometimes.
yeah, the sometimes
You
situation.
love sometimes. I
So
do
let's-
love sometimes.
Let's do exo again.
Sometimes are the
it's
ones that
tight.
are always on the tests.
So an exothermic reaction that gets more organized. Why do I S? It's supposed to be a 0.
Oh, what?
Because that's representing S.
Oh, that
That
makes
doesn't
so
make
much
any
more
sense.
I was so confused.
Sorry about that.
Okay, Taylor.
It's like
This
when you have a
just
math
shows how
problem,
much I-
and it's like if the answer is no, move on. If the answer is yes, then all this garbage.
So you know it's
The
yes.
answer is always
Every
yes
single
because they
time.
want you to do it.
That's funny. Why did you even ask that question? Okay, let's look at our problem here. So we're saying it's exothermic, so delta H is going to be negative. But now we're saying that the entropy is also negative.
So it's a negative minus infinity.
Okay?
It's a triple negative.
Bum, bum,
So,
bum. That means super emphasized in Spanish.
Mega super ultra.
the one piece of this equation we have control over is the temperature. So if I want to make this type of reaction spontaneous, or meaning giving free energy, what type of temperature situations would help that? Or if I want my final answer, if I want delta G to be negative, what type of temperatures do I want?
A really low one.
Why Taylor?
Oh wait, no, sorry, a really high one. Wait, wait, I'm thinking. I don't know. Now I'm really confused.
Don't
Oh, a
ask me.
temperature. Oh, okay, that's not related to delta S at all. Temperature, I think a really, if you want it to be negative, then a really low temperature, yes.
Good. Because in a sense, these combined are going to be a positive value, right? If I wanted to stay negative, I need this to be a very small positive value. And so these type of reactions are favored at low temperatures. If you're not at a low temperature, then it's not going to be favored and it's not going to happen. Can someone think of an example of a process that is favored at low temperatures and not high temperatures?
Water freezing.
There you go, freezing, right?
That would be
Freezing.
difficult when it's hot.
Yeah, just like, I mean, if you had tons of pressure, you could freeze at like 200 degrees.
That's true. But then in a sense, it's not happening on its own accord, right? 'Cause you're
It's like in
applying
the core of
force to
the earth, the stuff is solid because there's so much pressure on it.
it. Okay, what's our last scenario? Endothermic. And
It's the whole weight of the
These next
world.
two are like creepy stalker ones, where like one alligator is following the other.
so obviously this is the opposite where these ones are favored at high temperatures.
Start walking down the street, there's a crocodile following you.
Dude, well, I mean, if you're a crocodile, that would be an as good.
Now, I used a word when I was explaining there that I just want to preface, because when you do your reading tonight, the book uses this word a lot. And honestly, it's like how I was taught it, but it's kind of, They're trying to get away from using it in terms of gives free energy, and that's the word of something being spontaneous. They often describe that a reaction that releases gives free energy is a spontaneous reaction, which works, but that word often can be very misleading, or sometimes people come to wrong conclusions about it. But just be aware that's how our book kind of talks about it. So,
Wouldn't it be so scary to spontaneously combust? Like you're just chilling and all of a sudden you're on fire and
that
you're
would
dying.
be scary
I
because
don't
it
know.
just happened.
Well, yeah, I know. You kind of
Be like,
die.
oh,
I would be scared.
Be scared for the rest of us.
Yeah, no, that would be so weird if I just like all of a sudden like, zoom, and all you gotta like.
Dude, I'm reading this book, so basically the devil is basically getting a hold of the world, and so every once in a while somebody will just randomly melt. It's kind of scary. Yeah.
Hey,
It's a cool
you know
book.
what book is scary, man? Peter and the Shadow Thieves. It's like after Peter and the Starcatchers.
You have to sell me more.
It's like Dementors, but like very, very much more serious.
I don't want to do it.
You should read it though, it's good.
Okay, last problem for today. Last two smiley, well, let's start with one and if we have time for the second one. So last smiley face up for grab is let's solve problem A here. Now let me just preface a little bit what it's saying. Okay, so it wants to know, predict the direction in which delta G for the reaction with, so I need to change there's a typo on your paper. Your paper says without. You see that?
Just eliminate the out.
So change it to with. Okay, so I want you to start up just predict the sign of delta G without actually doing any math. Okay, I will tell you though that the delta H, it is an exothermic reaction. Okay, so it's an exothermic reaction. So knowing that it's exothermic and looking at the equation, predict the sign of delta G. Ready, set, go. You can talk to your table buddy if you want.
So it's more or less than zero. So it will be.
And then it's this has 4, so 2. Oh, so we have to provide us to do it. So it's a triple.
I don't know.
But
That's how excited I am. I figured it out. Positive.
So it's the H, so this is 2, or so this is 1.
But then
So it's 4 to 2, so.
more organized. Exactly.
Oh.
Favored. And since it's not favored, it is positive.
Well, if it's negative entropy, that means it's getting.
Yeah, so it just becomes a negative.
Yeah. Or no, negative entropy is more organized.
Whatever it is.
Negative, positive, negative, or what the heck, negative, positive, negative. So
It's
this
positive.
becomes a negative, so triple negative, these ones cancel out.
I want it to be.
According to the clock, we have
They are right on the dot though.
That's kind of sick.
They're all like control that. They can control the clock. Yeah.
These ones?
That would be
another one.
Yeah, dude, that would actually be hilarious.
So they
Yeah.
could like,
I don't know, but yeah, they somehow, because they're all like to the second on the bell. And then like when daylight savings happens, I don't have to do anything. They just,
are you sure somebody doesn't just come around?
Anyway, while we're talking about that, that means that we have 20 seconds. So I think we should.
It's positive.
but they're all synced like literally up to the bell.
Okay, wait, we need to go. Wait, let's go, let's go.
Okay, show me your sign really quick, positive or negative.
Oh.
Ooh, we're
I swear
split
it's
like
positive.
half and
Oh.
half.
It's positive.
Probably
You
is.
better be right, sir.
Okay, so we know delta H is negative,
Uh-huh.
It was 1 second off.
S is negative,
It's fine.
right?
Yeah.
So, without knowing the temperature, or if temperature, I guess they're saying temperature is increasing.
Oh, it's positive.
So the bigger this gets, the bigger the positive gets, which
Yes.
means it's most likely to be positive.
Oh, wait.
Okay, wait, we should clap.
Wait, but isn't there a negative?
3, 2, 1, here we go. That was lame. You all failed.
Because you're going from
You can have some clapping.
to 2
Oh.
How many? What did we tally at?
Okay, we'll pick up this where we stopped. I passed out your practice problem set. It's not very long. And then just some read.
What did we tally at, Gabe?
Okay? Come see me if you need any help today before you take your test tomorrow. Remember to take your test tomorrow.
Do you have to do that like now? Or where do we do it? What's going on?
I think we just have to do it before next class, and you have to have video evidence.
I don't have a phone. How am I supposed to have video evidence?
Get a phone. I don't know.